Good day, my name is Frank Purple, and welcome to an online video tutorial on enzymes. It is important to know that the only reason why I am sitting here and that you are watching this is that our bodies are powered by millions of little chemical reactions constantly going on inside of us. We are all but sentient test tubes bubbling away, and when we stop bubbling, let's not think about that. This constant series of chemical interactions going on inside of us and powering our flesh vessel is called the metabolism. The metabolic pathway is the order in which many of these reactions must take place. Think back to math class and BEDMAS. We must first complete the operation inside the brackets before we move on to the multiplication, just as the same way in which certain chemical reactions must occur before others. There are two types of metabolic reactions, with catabolic and anabolic reactions. A catabolic reaction involves the breaking down of a substance and the release of energy through the separation of a phosphate from the compound adenosine triphosphate, or ATP, into ADP, or adenosine diphosphate. On the other hand, an anabolic reaction involves the building up of a molecule through the synthesis of the phosphate and ADP into ATP. If you would like to learn more about how cells use energy, please consider watching my video on the topic. In order for a proper chemical reaction to occur, there has to be enough energy present within the system. This is indicated by this little bump on the graph right here, and is known as EA, or activation energy. The role of an enzyme is to help decrease the amount of energy required for a reaction to take place by holding the reactants, or the substrate, in the correct positions. This reduces the amount of energy required for a reaction to occur and effectively speeds up the rate at which said reaction can occur, allowing for more reactions. Each enzyme is specific to its substrate. For example, maltase helps break down maltose, lactase helps break down lactose. You can often tell which enzyme is associated with which substrate simply by the name, is that it will often be the name of said substance, but with an "ase" for the ending. All enzymes work like a hand, and that in order to properly grab the substance, it must properly bind the active site, or the palm of the hand. In this scenario, my hand is the enzyme water bottle "ase". In order to grab the water bottle, I must first ensure a decent grip on it, and then I must tighten my fingers, just as the same way the enzyme alters its shape after receiving a product in its active site. This method is called the Induced Fit model. A single enzyme can help produce multiple reactions in its lifetime, not at the same time, of course. Just so my hand still exists after I picked up the water bottle, enzymes are present both before and after the reaction, just like all catalysts. Like most good things in life, enzymes are made from proteins, and as such, are subject to their faults. All enzymes in the human body perform best at a temperature of 37 degrees Celsius. We can see that if the temperature gets too high, they will quickly fry up and become useless. On the opposite side, we can see that although they may not become destroyed, lower temperatures will cause the enzymes to move slower, causing a reduction in the reaction rate. Please note that enzymes serve to increase reaction speed, and as such these reactions will always happen on their own, regardless of temperature. As such, the reaction rate can never reach zero, except at absolute zero, or 0 degrees Kelvin, at which nothing moves and all chemical reactions are impossible. Unlike temperature, different enzymes work best at different pH levels. The pepsin in our stomach works in a more acidic climates, while the maltase works better in more basic ones. Please note that if pH is too low or too high for an enzyme, it will be fried and unable to work or receive worker compensation. Also, please note that pepsin, despite not containing an "ase" in its name, is an enzyme. These enzymes are pretty sneaky. Stay alert! Assuming the concentration of enzymes is constant, if there is nothing to react with, no reaction will occur. We can see that the more substrate we add, the higher the reaction rate goes, until the enzymes are maxed out with work, at which point the reaction speed caps. At least they know not to overwork themselves. If there were infinite enzymes, this graph would continue to rise until it exceeded the digital canvas on which I created it. Alternatively, We can see that by increasing the concentration of enzymes, assuming infinite substrate, that this graph will also continue to rise until the end of time. Now, since enzymes are blind, they cannot see what they are grabbing. Competitive inhibitors fool enzymes by pretending to be substrate, so that they waste their time, causing them to try and react duds. As such, more actual substrate is required to drown out these fraudsters and achieve the maximum rate. Non-competitive inhibitors are sneaky little buggers that bind to the allosteric site of an enzyme. Imagine if someone grabbed your hand. It would be pretty hard to pick up things properly. No. This lowers the potential maximum rate by putting enzymes out of commission. Some enzymes need a helping hand to do their job. Cofactors will help bind to an enzyme, allowing it to effectively manipulate its desired substrate. It's like having to get someone else's thumb if you wanted to pick something up. There are two types of cofactors, with inorganic ions and organic non-protein cofactors, also known as coenzymes. After watching this video lesson, you should now have a clear understanding on how enzymes work and how various conditions affect their performance. Please use this information for good and not for evil. Thank you! Mm.